All right, section 6.3, multiplication and division of rational numbers. So as we start this particular section, we're taking a look at the definition of multiplication. And the definition of multiplication you've seen before. You multiply across the top for a fraction, you multiply across the bottom. As we did this, we ended up with two different diagrams that we were looking at. These two diagrams involved taking a rectangle, splitting it into 5, we'll call them columns down, and then 4 rows across. Depending on how we do our shading, we still end up with the same double shaded area. In the double shaded area on the first diagram, the double shading of 9 is actually our solution, and then the total number of rectangles of 20 is the denominator for our solution. And then on the second diagram, the way we were thinking about it was more along the lines of we only have those blue pieces left. That's only 3/5 of whatever we had originally left. And then we shaded 3 out of 4 of those location pieces or whatever, and we ended up with 9 out of the original 20. There are several properties that we had taken a look at. The multiplicative identity, which just says that the number 1 is able to be multiplied by anything and doesn't change the quantity value. The second is the multiplicative inverse, which says that for every non-zero number, there is a unique value that is the reciprocal, so that when we multiply things together, we get back to the number 1. Our third theorem for the day was the distributive property of multiplication, and it's over addition or over subtraction. And for other reasons that are just calculation based, we might simply want to be able to do a multiplication before we do an addition, so this is a very nice property to have. The multiplication property of equality is actually what allows us to multiply two values that are the same, so something like an equation, by the same value on both sides. So that a over b is equal to c over d. We're allowed to multiply both sides as long as we multiply by the same value, e over f. And then on this one, we were taking a look at the property of inequality. And the idea being that if we multiply by something that's a positive number, the sign, the direction of their inequality stays the same. And if we multiply by something that's negative, like in the second example when I multiplied by -2, it actually changed the direction of my inequality. And showing this happening with numbers is a pretty straightforward way to do that. Our last one was the multiplication property of 0, which was super exciting. If you multiply by 0, you get 0. All right, so we were at this point, we were on this process of multiplying. You guys had told me we were going to multiply by 4 over 3 on both sides. We know why it's 4 over 3 because that's the multiplicative inverse. But what is it that allows us to multiply by the 4/3 on both sides? Right, that's the multiplication property of equality. Okay? So we've got the multiplication property of equality. We used the multiplicative inverse, and we ended up getting 1x equals 1, not 1 anything, 1x equals. And then we're going to have to simplify the right-hand side. So what do we get when we multiply 1/5 times 4/3? 4/15. And the ability to do just that was actually a definition. That's just the definition of multiplication. That's what we had on the very first slide of the day. Now, it sort of looks like it's done. The reality is you're really not quite done. It really isn't 1x. We really want it to say x equals 4 over 15. And often people jump from here, obviously, to here already anyway. But recognize when you do that, when you change 1x into x, what property are you actually using? That's the identity property, actually. It's hidden. We don't usually see it actually written out, but I wanted to show you it written out so you'd recognize that it's there. This is the multiplicative identity property. And that's it. That's all the properties that we had on this particular problem. Any questions on that one? It's kind of crazy, though. We had 4 properties. And in all honesty, most of you probably could do it in one step written down. And you used 4 properties. Cool, huh? Well, you can't do this one in one step. Nice try. Won't always work. This one's a little more complicated. Not only do we have some fractions like we had in the last one, we also got some addition and subtraction going on. Now, there are lots of ways to start this problem, so you guys are going to direct the show today. What in the world would you like to do when you do this problem first? Okay, So we have a minus 1/4 from both sides. What is it that allows you to subtract 1/4 from both sides? That's a property of equality, right? And it's actually the additive property. I know it's subtraction, but we sort of include it in there. So this is the additive property of equality. And when we subtract the 1/4 from the left, this piece right here becomes what value? It becomes 0, right? Yeah, we still have the 2x over 3. I just mean the part that I circled. The part that I circled becomes 0, yes? Why? Okay, but what property? I should say it differently. What property is that we used?
Inverse?
Yeah, it's an inverse property. Again, it's the additive inverse property. The reason we picked the 1/4 and the negative 1/4 is because they're additive inverses to each other. So this is the additive inverse. And I will avoid actually writing the 0. But in avoiding actually writing the 0, the hidden step that I'm using is the additive identity. Because adding that number 0 to the 2x over 3 just still results in 2x over 3. Are you guys all with me? It's not something we usually write down, but it's there. All right, I still have an x over 6, and now I have a negative 1/2 and a negative 1/4. What would you like to do next? Combine those. Okay, so as we combine those, what are we going to do to combine those? Common denominator, you're going to make the...
Of the 1/2 to 4.
Okay, so like make this one 2 over 4. Does that work? Okay, sounds good. So we're going to have a 2x over 3 on the left. I have x over 6 on the right. What is negative 2/4 minus 1/4? Minus 3/4, negative 3/4, right. So I did a lot of simplification there, right? And when I was doing that simplification, those were the definitions of addition, or definition of subtraction, actually, technically. So this is the definition of, not of twice, of addition or subtraction, depending on how you thought through that. Now what? Okay, so we're going to do the same kind of thing, but with the variable term now, minus the x over 6. I still have a negative 3/4 on the right. But now I have 2x over 3 minus x over 6. Now, this subtracting the x over 6 to the other side, that's actually the same one that we had before. That's the additive property of equality. And when I do that, I get this to be 0 right here, right? That's the additive inverse property. And then that 0 adding to the negative 3/4, becoming negative 3/4, that's the additive identity. So I'm using all these same 3 top ones again when I did that. All that was happening a second time. All right, now what are we going to do with the 2x over 3 minus x over 6? All right, common denominator, multiply by 2. I see here both those things going on. So something like this. So now I have, on the top, this is 4x over 3 on the first fraction, and then over 6, and then I have x over 6 in the second fraction. What does that give me? 3x, actually. Be careful. And then over 6, yeah. So remember, when we're subtracting quantities that are alike. They still have the x involved. All right, it's like saying 3 apples minus, what was it, 4? 4 apples minus 1 apple is 3 apples. It's not 3. It's 3 what? It's 3 apples, kind of like that. And then you can reduce that, right? So what does 3x over 6 reduce to? 1/2 or x over 2, either way. Okay, so what we've done here is we've done some definition of rational numbers, like what we did on the very first day in section 6.1, actually, to simplify. That's what we've done. Now what? Divide or multiply? Multiply. Okay, good. So we're going to multiply both sides by 2 over 1. Why 2 over 1?
Let
Okay, so a few things. First, what allows us to do the multiplication? First, it's a multiplicative property of equality. That's what allows us to multiply. Then, what we're choosing to multiply by is because it's the multiplicative inverse. And then, what we're about to do is we're about to recognize that 2 over 1 times x over 2 is actually just x, not 1x, right? And the reason we recognize that is because that's actually the multiplicative identity that's at play. So we end up with x on the left, and what is our answer on the right? It is negative 3 over 2. Now, some of you might look at that and say, wait, it's negative 6 over 4, and that's true, but it will simplify to negative 3 over 2 if you don't recognize it earlier in the problem. That's quite a list of things that we did, right? They're not exactly listed in a specific, like, pointed order at this is the place where this happened. We used the first 3 twice in the process as well, which is interesting. Any questions on this one? Okay. Next, we're going to look at division of rational numbers. So if a over b and c over d are rational numbers, and we want to divide them, a over b divided by c over d equals e over f. This will be true if and only if e over f is the unique rational number, such that c over d times e over f equals a over b. And again, we're going to do this with some numbers because it looks really weird, but it's really not that complicated what it's saying. Okay, so this is saying that if I had, and we'll use whole numbers, 6 divided by 2, then I know the answer to this is 3. But the answer to this is 3 if and only if I were able to take 2 that was being divided times the 3 that I'm getting as my potential solution, and it equal to the 6 that I'm getting at the end. And this is really how kids usually start to learn division and even subtraction to some degree, is the idea of, well, you learn your multiplication tables first, so you know that 4 times 9 is 36, or whatever fact you're looking at. So if you're asking yourself what's 36 divided by 9, you go back to your multiplication tables and you say, well, what times 9 is equal to 36? Okay, that's what we do. And so that's the definition that your book is using for the division of rational numbers. Now, in reality, when we're working with them, we'd like to know how we go about actually doing the process of division. That's what this theorem's talking about. This is the algorithm, or the process by which we do division of fractions. If we have a over b and c over d and they're rational numbers, and the c over d is not 0, then a over b divided by c over d is the same as a over b times d over c. So let's just talk visually what happened, and then I'm going to show you why this actually works. What visually happened to get from here to here? It's a multiplicative inverse, or sometimes it has another name too that we hear it called. Reciprocal. You'll hear somebody call it reciprocal sometimes. Very much less mathematically precise. Some people will call it a flip of a fraction. But yeah, you're using the multiplicative inverse, and you're changing what else? The operation in between, right? So originally it was division, and now the operation's actually multiplication. And in some sense, that's very friendly because we already have all these rules and everything for multiplication. Now I don't have to create new ones for division, right? I just turned it into a division from a division problem into a multiplication problem. Okay, but I want to show you why this works because it sort of looks like magic. I mean, like, right? You're just going to switch it around and turn it into a multiplication, like, fancy, but, like, why in the world would that just work? It seems a little bit strange. And so it actually works, and I'll show you, and you could use numbers if you were trying to show this to a younger kid. We're going to go with the letters that we've got here because it's not too bad for us. But if we have a over b divided by c over d, which is where we're starting, what I'd like to do is I'd like to write that as we call them a complex fraction, a fraction inside of a fraction, like this. Okay, so the first fraction is divided by the second fraction within a bigger division sign, like a fractional form. Okay, everybody good so far? Okay. Well, obviously we don't like answers in this form, so even when we get answers and things like this, we tell kids, like, don't leave them like that. So what we're going to do is we're going to try to eliminate the fact that we have a fraction inside of a fraction. And so we're going to do that by taking a look at the c over d and saying, okay, that's got to go away. It's kind of like when we had, the 2 over 3 times the x. The 2 over 3 has to go away. So what do you do to get the 2 over 3 to go away? Well, you multiply by the reciprocal, right? So what I'm going to do is I'm going to multiply this denominator by d over c, the reciprocal. But if you multiply the denominator of a fraction by something, you got to do it to the numerator. Like so. Everybody good so far? Well, the whole point down here is that when we multiply these, you get 1. They were multiplicative inverses, which means I'm actually left with a over b times d over c. And that's all there is to it. It's really not a trick at all. It's just what we look at visually that looks different. Okay? So, that is the multiplicative version of division, basically. All right, we're going to talk a little bit more concretely about actual problems, but maybe a little bit more abstractly about why something works. So, there are 2 ways to think about what it means to do division. So let's say that you have 6 objects. So draw yourself 6 objects, all the same, so that our argument can be the same. Make sense of it. Mine don't look like they're the same, but just pretend for the moment that they are, okay? What does it mean? What would it mean to take these 6 objects and divide them by 2? Physically, what would you do? Okay, so one way of doing it is to take the objects and to cut them into 2 groups. Okay, so you've made 2 groups of 3 objects. There's another way to do it. You could do 3 groups of 2 objects. So you could do 2 objects like this. So you get 3 groups of, and I'm going to change my language just a little bit because it's going to make it easier in a minute, of size 2. Do you guys agree? This is 3 groups of size 2. These are both legitimate ways of arguing what division looks like. The one that's the most helpful to us right now is the second one. This is the one we're going to focus our attention on. Division is making groups of a certain size. So why does it matter? Well, the reason it matters is because if you take a look at my next problem, it says we want to divide by 1/2. Dividing by 1/2 is not the same as dividing by 2. And if we use the first example of making groups in this way, it says I need to have 1/2 groups. And that's very awkward. But if you make it the second way, it's saying I want to figure out how many groups I have of size 1/2. So what could I do to my red objects? We'll say they're cookies. What could I do to these cookies to make groups of size 1/2? I can take each of my cookies and make them half cookies, right? So, in some sense, I'm splitting them or dividing them up into pieces. So I now have half sizes or something of that nature. So I now have groups of size 1/2. How many? There are 12 groups of size 1/2. Whoops. 1/2. Now, the cool thing is that what that actually did is that took the value 6 divided by the value 1/2, and it gave you a very concrete picture form for why in the world it should be true that 6 divided by 6 divided by 1/2 is the same as 6 times 2 over 1. Because this answer is supposed to be 12, correct? And 6 times 2 is 12. And this is a picture diagram for why that would actually work in a very small scenario. So that's also a justification for why that happens. All right. The last part of this section feels a little bit like we're deviating from the description in the title, but it isn't. The last part of our discussion is going to be talking about exponents. So the reason that that actually works within what we're talking about is because all exponents are is just repeated multiplication of something. If you multiply 3 times 3 times 3 times 3 times 3 times 3 times, I don't even know how many 3s I just said, but a whole bunch of 3s, that's okay, but there's a shortcut way of writing that, and that's to write the 3 with an exponent on it. So that's why this is included in this section. For a rational number a and a natural number n, so remember natural just means counting numbers like 1, 2, 3, 4, and so on. A raised to the n power is a multiplied by itself n times. That's what exponents actually are. And there are several, we'll call them properties of exponents. They are properties in the sense that they hold true all the time, but they're not just like somebody told them to you, it works this way, and you have to believe them. They're all things that I'm going to show you why they work. So that actually makes them theorems because they are provable. Okay? So the first one that you see on here is you see a to the m times a to the n. Do you remember what you do when you have multiplication like this? You add the exponents. That is exactly correct. So if you add the exponents in that scenario, what would you do on number 2? You subtract the exponents. How about number 3? This is multiplying the exponents. I promise I'm going to tell you why all this works. Any idea what number 4 would look like? Yeah, it looks and feels like it's some kind of a distribution. A to the m times b to the m. How about number 5? Good. A to the m over b to the m. So again, it feels like a distribution. What's different between 5 and 6? Yeah, so you're already ahead of me. The difference is the negative, right? And the way we deal with the difference is, say that again.
You have to flip the fraction to
Right.
get rid of the negative.
Yeah, so that negative exponent actually flips the fraction upside down. So it's going to be the same thing we had on 5, but flipped upside down. B to the m over a to the m. So far, so good? Okay, so we're going to do, I always have students who get a little bit confused as I start this process. I'm showing you how to explain these theorems. I am not asking you to do this all longhand out when you do the problem. That is not the point. The point is that sometime, somewhere, someone along the way is going to ask one of you guys or more than one of you guys, well, but why do you add them instead of multiply them? And I don't want you to look at them like a deer in the headlights and go, because my math teacher told me so. So I'd like for you to be able, and if you can't do it on the spot, you can just say, you know what, that's a great question. Let me talk about that tomorrow when I have some more time. And you can go back and you can find that information. So I want you to know that you have that at your disposal. So we're going to take a look at some of these properties and why they work. All right, so we're going to do them one at a time. The first one you typed are the ones who told me. This is a to the m plus n, right? Very quickly, you can justify this, again, using some examples, by doing something like a to the third and a to the fourth, just picking up some numbers. You can remind the student that a to the third means a times a times a. There's 3 of them. And a to the fourth means the same thing 4 times. And if you take a look at simplifying what this is back into exponential form, this is a to the 7th. And then you can ask the student, how did you get from 3 and 4 to 7? Well, you have to add them together. So this shows exactly why addition works in one case, okay? This is not a proof by any stretch of the imagination, but it does give justification that's pretty good. We can do the same sort of thing on this one. This one's supposed to be subtraction. So if we're taking a look at this one, we can do an example, and we can say, okay, well, let's use maybe a to the 5th over a squared. Well, what is a to the 5th? Well, it means I've got 5 a's. What is a squared? Oh, well, it means I have 2 a's. And then what can you do? All right, you can divide these out because they match, right? So this leaves you with a cubed. Well, how do you get from 5 and 2 to 3? you subtract. All right, the third one, a to the mn. So this one you had told me was supposed to be multiplication. You multiply these together. So let's do a cubed squared. This is one of the ones that students do often get confused. They often will want to tell you this is a to the fifth. That is a very common mistake. Well, squaring, the square on the outside means I've got the a cubed twice. And then the a cubed means I have a 3 times. And I've got it twice because I've got 2a cubes. So in the grand total of this is that I have how many a's? 6. And how do I get from 2 and 3 to 6? Multiply. Number 4 was a to the m, b to the m. And on this one, we will do to the third. So what this is actually saying is that I need AB times AB times AB. And because we have commutativity and associativity, which allows us to move the A's and the B's around, we can actually sort of group like things together because it's all multiplication and say this is A cubed, B cubed. And comparing that back to the original value that we were starting with, that looks like distribution, right? This one's perhaps even cleaner, a to the m over b to the m, because there's really not even any multiplying out that you have to do. So if this was a over b cubed, you have a over b times a over b times a over b. And with your properties of rational numbers, you can multiply across the top, so that's a cubed. Across the bottom, that's b cubed. And again, you have that same sort of a distribution feature going on. All right, the last one of this particular set, and we've got 2 additional similar ones down below, but the last one here has that negative exponent. So one of the things we can do at the outset is we can separate this negative m into being negative 1 times m, right? I mean, that's what negative m means. It means it's a negative 1 times an m. Well, why is that helpful? Well, it's helpful because I can actually separate it like this using a previous property in reverse. Right? Instead of writing negative m, I can write it to the m power, and then I can write it to the negative 1 power. And that's exactly property 3 used sort of the other direction. Well, that's nice because this piece that's inside right here raised to the m power, I already know what that is. That's from property 5. So I'm allowed to use the previous properties in justifying why this works. I guess I'm justifying this for you already as it is without any numbers. My apologies, but we'll be okay, right? Yeah, okay. So we have b to the m, I'm sorry, that's the wrong, a to the m over b to the m. That's just from property 5. That negative 1 exponent, though, needs to be dealt with. And that negative 1 exponent has a sort of definitional sense that I haven't written it down in class per se, but this idea says that it's a reciprocal. It means to do reciprocal. And the reciprocal here is going to be also known as our multiplicative inverse. So when I do the reciprocal, it flips things upside down. So it takes that a to the m and moves it down, and it takes the b to the m and it moves it up. So we have b to the m over a to the m. Are you ready to see my favorite one? My favorite one is a to the 0. A to the 0, do you guys remember what it is? It's 1, actually. So if many of you don't remember what it is, which is fine, it's one that people have a hard time with justifying because it looks really strange. I mean, the natural thing would be to think that it was a or 0 because at least there's an a and a 0 already in the problem. Why in the world should it be 1? Well, let's actually take this and write it in a little bit different way. So I'm going to take a to the 0, and I'm going to write 0 in a funny way. I'm going to write 0 as, and we'll use numbers just because I can, 5 minus 5. Now, that's a really weird way to write 0, but it's 0, right? Yeah, okay. So let me put that at the very beginning. A to the 0 is the same as a to the 5, minus 5. We're going to use property number 2 in reverse. That is, a to the 5 minus 5 is the same thing as having a to the 5 divided by a to the 5. Isn't it? Yes, it is. But what is anything divided by itself? It's 1. It's 1. 5 divided by 5 is 1. Yeah? And look at that. A to the 0 is equal to 1. And that's an actual real proof. If we didn't have the 5s there and we put m's there, that would actually work. Like a real legit proof. See, you can go tell somebody you proved something mathematical today. Exciting stuff. All right, our last one is very similar to the one that we had done just before on number 6. It says if we have a negative exponent, a to the negative n like that, this is 1 over a to the n. There's several ways that you can argue this. One of the ways that you could argue this is that a to the negative n is the same as a to the 0 minus n. That way actually works really well because I can kind of do what I did back on number 7. I can write this then as a to the 0 on top and a to the n on bottom. And we just found out just a minute ago that a to the 0 is 1. So that's actually a really nice way to do it. There's a couple other ways to do it, but I'll spare you the details. Okay, so all of these pieces right in here are properties and theorems and how we work through them, but that's not the problems you're going to be doing. That's my gift to you for the future teacher in you, okay?